A translation like this one is often referred to as a slide in a plane. While that term isn't very mathematical, why do you think that term might be used? Think about that as you work to answer your lesson question. How are translations described mathematically? Next, you're going to learn more about the properties of a translation.
Here is the formal definition of a translation. A translation is a rigid transformation or isometric transformation that moves every point of the pre-image of an object the same distance and direction to create the image. The pre-image is the geometric shape before a transformation, and the image is the result of that transformation. Now, keep in mind that in a translation, every point moves. That is unlike a reflection, where any point on the line of reflection would not move. I also said that this is a rigid transformation, which means that the size, the shape, and the measurements of lines and angles all stay the same. Let's look more closely at that. Translations preserve angle measures. Angle, BAD, in my pre-image is congruent to angle B prime, A prime, D prime in this image. Also, the length of the lines stay the same. Line segment AB in my pre-image is congruent to line segment A prime, B prime in the image. The shape also stays the same. You can see that both of these shapes are rhombuses and the same size. The shape hasn't gotten larger or smaller. Lastly, the orientation stays the same. That means the shape doesn't rotate or do any backflips. Now, there's one other important piece to keep in mind about translations. When I connect the vertices of the image and the pre-image, you're going to notice an important pattern. First of all of these line segments are the same length, and that's because each point moves the same distance. Also, these lines are all parallel. That's because each point moves in the same direction. You can also map how these points move. Point A moves to the left and then down to become A prime. And the same pattern applies to all the other vertices. Next, you're going to examine translations more.
You're working to answer the lesson question, how are translations described mathematically? Now, so far, you've learned the formal definition for a translation, and you know the properties that are preserved under a translation. If I were going to translate this shape, it'd be like I was sliding this shape to a new location. And you now know that these line segments that are connecting the vertices of the pre-image to the image are all the same length and are parallel to each other. Now, if a translation is performed on a coordinate grid, well, you can use coordinates then to describe the translation, and we'll explore that next. On a coordinate plane, you can represent or express a translation by a function that takes an input of a coordinate and maps it to an output of a new coordinate. Now, a function is when one input maps to exactly one output. So you may be familiar with functions where the input is a single number. In the case of translations, the input is going to be an ordered pair. And the output will also be an ordered pair that may be written like this. And in this case, the A is the number of units translated horizontally. If A is positive, that means the shape is going to move to the right. And if A is negative, the shape is going to move to the left. And B is the number of units translated vertically. So if b is positive, that means the shape moves up, and if b is negative, the shape is going to move down. Now, there are a couple different ways that you can notate a translation. The first is using a function rule, which will be written out like this. So think of the t as representing translation, and here are a and b values. You can also use a mapping rule. So in this case, you'll begin with a coordinate, and that translates to a new coordinate. And notice that the new coordinate includes our a and b values. Now, both of these notations mean the same thing, and you might see them used interchangeably. And also keep in mind that even though it sounds like a translation happens by moving horizontally and then vertically, in reality, a translation is moving along rays that are parallel to each other. Let's actually take a look at a translation on a coordinate plane. So now that we have a coordinate grid, it's easier to see how a translation moves. So let's take a look at this example. What is the image of triangle JKL after the transformation xy to x minus 5, y plus 4? All right, so this means that the x values on all the vertices are going to be moving to the left 5 and are going to be going up 4. All right, so let's begin with one vertex. Now J is located at 2, 1. I need to translate it now to J prime. So that's going to be at x, or 2, minus 5. And it will be at y, or 1, plus 4. So if I simplify this, I now can see that J prime will be at negative 3, 5. So let me add that to the coordinate plane. Here's J prime. Let's do the same with the other vertices. So K is located at 6, 0. I'm going to translate that to K prime. So I'm going to begin with x, 6, minus 5, so that's 1, and y is 0, plus 4, so that's 4. So let me add that as well to the coordinate plane. And let's also take a look at L. So L is located at 2, negative 1, which means that L prime is going to be at 2 minus 5, negative 3, and negative 1 plus 4, 3. And I can add that as well to the coordinate plane. But remember, we're not just working with vertices, we're talking about translating a shape. So I need to connect those vertices together so I can see my image. And I can see now that the image is the same shape, the same size, the same orientation as the pre-image. In fact, each of these vertices moved the same direction and the same distance. So this is a translation. Also keep in mind that if you forget the rule to add to the coordinates, you could also just count to the left 5 and count up 4. Now, you're ready to determine translations on a coordinate grid. Let's take a look at this question. What rule describes the translation from the pre-image to the image? Well, I can see I have two figures on the coordinate plane here. I need to identify the pre-image and the image. Now in this figure, I can see that the vertices are all given in prime notation. So that tells me that this is the image. The other figure, which overlaps this one, is the pre-image. Now I can see that the shape, size, and orientation are all preserved. And if I connect corresponding vertices, I can see that each vertex in the pre-image moves the same distance and direction to become the corresponding vertex in the image. So this is a translation. Let me go ahead and think about creating a rule for this translation. I'm going to focus on just one vertex. Let's see how Q translates to Q prime. Q is located at negative 1, 4. It translates to Q prime, which is located at 1, 5. Based on this, let's create a mapping rule. So for a mapping rule, I'm going to take any point x, y, and translate it to a new point. Now, if I think about my x values, at point Q, the x value is negative 1, and at Q prime, it's 1. Let's move 2 units to the right. So that means I'll need to add 2 to any x value. And for my y values, Well, in Q, I began at 4 and then moved up 1 unit to 5. So I need to add 1 to any y value. Now I have my mapping rule. But let me go ahead and check this rule by using another vertex. So let me begin with T. T is located at -1, 1. Now to translate to T prime, I'm going to use the mapping rule. So I started with -1, and I need to add 2 for my x value. And I started at 1, and I need to add 1 for the y value. If I go ahead and simplify this, T prime should be at 1, 2. And indeed, that's exactly where T prime is. So I can tell that my mapping rule is correct. Now keep in mind, I can also write a function rule for this translation. That function rule would be this. Move to the right 2, up 1. All right, now you are ready to write a rule for a translation. Now let's take a look at this question. What is the pre-image of the figure if the rule that created the image is this? Now notice what this question is asking. We have a figure here, but this is the image after the translation. We have the rule that created this image, but we need to work backwards and find the pre-image. To do this, we're going to need to use some inverse operations. Let's begin by focusing on one vertex. So J prime is located at -4, -1. Let's work backwards so we can find point J. Now, if we think about the x value for J prime, which is -4, that was found by subtracting 7.5. To work backwards, though, we're going to use the inverse operation. We're going to add 7.5. So we'll take -4 plus 7.5. Same for the y value. In J prime, the y value is -1. Instead of subtracting 4.1 from the rule, we're going to add 4.1. So we have -1 plus 4.1. Solving this, that means that point J is at 3.5, 3.1, which would be about right here on the coordinate plane. Let's take a look at the other vertices. K prime is located at -3, 1. We're going to work backwards to find point K. So we take -3, we're going to add 7.5. So that's going to give us 4.5. And we're going to take the y value from K prime 1. We're going to add 4.1, the inverse operation. That's going to give us 5.1. So K is located about right here. And finally, let's take a look at the last vertex. L prime is located at -2, -4. Now, if we think about finding point L, we're going to begin with the x value, -2. We're going to add 7.5, so we get 5.5. If we take a look at the y value for L prime, that's -4. We're going to add 4.1, so we get 0.1. And so L will be located about right here. Now, if we go ahead and connect these vertices, we will see that we now have the pre-image for this translation. All right, now you're ready to try one on your own.